Yeah, okay. So, we can continue to discuss because I think we have a lot to discuss. Yeah, sure.
¿Alguna otra pregunta?
Thanks again for really a very nice presentation. But I find that your comparison between the real time as in the sub-picosecond electron transfer story, that these let's say you showed this as if there is a kind of contradictionary between the real-time TDDFT on one side and the Marcus theory on the other side. I mean, in reality, it should be so that the real-time TDDFT, when you propagate long enough, should go into the result of the Marcus theory if it would have the right asymptotic limit. And the point there is here that if you propagate real-time TDDFT longer and longer and longer, you do not fall back to the Born-Oppenheimer picture. And you have these kind of divergence. And as long as you propagate for 3-10 femtosecond, it doesn't hurt you really. But I think this is a beautiful example where actually something which happens super fast at a point enters on the time scale of some chemical action. And how do you think to overcome these problems that you can go from the real-time TDDFT really at the end into an adiabatic Born-Oppenheimer picture?
Oh yeah. So just I was not trying. Means that I was not clear. But for me, there is no contradiction. There are two possible mechanisms taking place on different time scales, and I have two different methodologies to address them. Well, now about your point, technically, in fact, so purely real time, I think we need Ehrenfest MD at least to move the nuclei also, because Marcus theory is nuclear motion driven. But effectively, so we will have a problem of computational cost. For the moment, it's not, we cannot reach one. No, we would be able to do picosecond, but anyway, the Ehrenfest MD is intrinsically flowed by the absence of electronic decoherence. So you would stay always on the superposition of state, and you will never decay like this without correction to a diabatic, diabatic or a ground state for one of the two electronic states. So it has to be corrected. So one thing that could be done would be to introduce electronic decoherence correction. So you have either you work with very sophisticated schemes, the exact factorization, this type of things, but it's completely unapplicable to this type of system. It's really expensive. Otherwise, you have this Toulard developed, I think, a decay of mixing methodology. But basically, you need to know the electronic spectrum during your simulation, and with some random criteria or Monte Carlo criteria, you induce artificially the collapse of the density of the wave function on a given constant state in this case. So I think that's something we could try to think about with, especially with nature. To have the spectrum and to drive after. We would need also tools, for example, to look at when we think that the system is going back to the ground state or is about to be back on the ground state. And when this is taking place, probably a few hundreds of femtoseconds after the excitation, we could start to operate this type of transition to, for example, to the ground state smoothly. For the moment, the few people who are doing this type of thing, they stop, they are Ehrenfest MD, and they continue with the UMD. So with all the potential and energy discontinuities you can imagine, but that's what we do for the moment, what people do for the moment. So it would be good to have at least a continuous scheme.
¿Alguna otra pregunta? Agradecemos la presentación del doctor Aurélien.